The keyboard raising.
Hello everyone, my name is Sarah. I come from Queen's University, Belfast, United Kingdom. I'm going to talk about how I have used machine learning to kind of create a meta-heuristic algorithm that does per instance algorithm selection on the subgraph isomorphism problem. So before I go any further, let me introduce the subgraph isomorphism search problem. We have two graphs here. One is the small pattern graph on the left and the other is a bigger data graph on the right. And my problem is whether the smaller problem exists within the larger data, smaller pattern graph exists within the larger data graph. Right? So we see one instance here that it does exist. So this is an NP-complete problem, and being an NP-complete problem, it requires a search in a search tree, and various heuristics have been proposed that clones the search tree using different techniques, right? So the heuristic, there are essentially three steps. In the first step, they reduce the search space. In the second step, a ordering is made on which I am going to do this matching. So I have shown two orderings here. On the left, I have highest degree first. So in the pattern graph, you can see U1 and U2 has highest degrees 3 each. So those are prioritized on the left. On the right, the lower degree, that is U0 and U3 are prioritized. And based on the ordering that we have, we get different size of the search tree, essentially different runtime execution. And so based on these three steps, we have many heuristics. We study 8 heuristics in this study. These are CECI, CFL, DPISO, QuickSI, RI, TurboISO, and VF2++. And we do our experiment on a HPC called Kelvin 2 on a AMD processor using 4 GB of RAM and a 30 minutes threshold. Because it's NP complete, we don't know how long it's gonna take, so we need to have a threshold. So we have it for 30 minutes per instance. So we have run our experiments on 8 different data sets. This range from patents data set that have 3.7 million vertices to small data set like IS that has 3,000 vertices, right? And the graph on the right shows how many, each of these data set has one data graph and 1800 pattern graphs. So the graph on the right shows out of these 1800 pattern graphs, how many completed execution within the given threshold. Okay. So, given this data that we have seen a few observations. Number one, we studied 7 heuristics, right? So, out of these 7 heuristics, is there any heuristic that shows the best performance across all these pattern graphs in all these data sets? No, it does not. So, each problem instance across each data set, different heuristics may show the best performance. We do not know beforehand which is going to show the best performance. What this graph on the right shows is on the blue, for each data set we have which heuristic has shown the best performance in that data set, what is the runtime of that data set. Now we propose an algorithm called the Oracle algorithm. The Oracle algorithm is a hypothetical algorithm which would know for each pattern graph in each data set which is the best heuristic for this particular pattern graph. So if we had that Oracle algorithm, then the fastest was in yellow, the blue is the Oracle, right? So we get a speed up. So here is the research question in this paper. Can we use machine learning to approximate the Oracle algorithm? Right? So in order to do machine learning, we need a certain number of features, we need features. So we have three type of features. The number one is graph feature. Graph feature, we started with 25 feature, ended up with selecting these 14 features because we did variance based thresholding or linear correlation to eliminate these features that we have. So we started with 25, we settled on this 14 graph features. Then we have level features. Level feature, like the graphs that we have, they will have levels associated with them. For example, if we have IMDb dataset, the levels might be this person is a actor, some person might be a director. So actor would be a level, director would be a level. Here the levels are represented as colors, and we have this level factor that counts how many occurrence of each color is there in the graph, both data graph and pattern graph. Now, unlike the graph features, we have taken 14 graph feature, so the size is 14 of that feature vector. Here we have 8 different data sets. In the WordNet data set, we have a level vector of 5. In the HPID data set, we have a level vector of size 307. Okay, if we take this entire level vector of 307, we will suffer from the curse of dimensionality. So to avoid curse of dimensionality, we have done feature reduction using dimensionality reduction using PC, right? So we ran PCA, we did the thresholding using the elbow method, and ended up with a smaller number of dimension of the level feature. The final features that we have is the graphlet feature, and this is the primary contribution in this paper. Graphlets are small recurring subgraph. These are also called motif, and they occur with a higher frequency in any large data graph, and they are different than graph features because graph features, two graphs having the same, say, vertex count, having the same edge count, may differ internally in their substructure. So, graphlet feature can be used to create a profile of the internal substructure of the graph. Right? So, this is the third type of features that we have. We have taken the count of these 17 graphlets shown here. Okay. We are going to use machine learning to do classification essentially. Why classification? Given a pattern graph in each of these data set, we want to classify which heuristic algorithm is going to show the best performance. Right. Now classification has different evaluation matrices like MCC, F1, precision recall, accuracy, etc. But that is not sufficient for us. Why? Because in a certain pattern graph, two heuristics may have the same fastest execution time when we are calculating the execution time using, say, millisecond level granularity. Okay, so we want to see, using this meta heuristic that we have created using machine learning to do heuristic selection. Okay, we want to know whether this results in a speed up across the data set. So instead of using this classic evaluation matrices, we have defined a evaluation matrix called the effective speed up. So essentially what we do is we check, compared to the fastest heuristic for a particular data set, this meta heuristic, how fast is it compared to the fastest. Alright? So we have one constraint. We had this hypothetical Oracle algorithm that knows what is going to be the fastest. So Oracle would be, our meta heuristic cannot be faster than the Oracle. Right? So we have that. It's constrained by the Oracle. And if our meta heuristic is as fast as the fastest heuristic, then we will have this effective speed up equal to 1. Okay, so across this 8 data set in which we tested, We use multiple machine learning algorithms across all different types of machine learning algorithms, lazy evaluators like KNN, tree-based solution like decision tree, random forest, AdaPost, extra trees, neural network. We have support vector machine, and yeah, we have 15 different machine learning algorithms with which we tested using all the 3 different features, the combination of these features. So we see that apart from 2 data sets, that is the word net and the is data set, we are getting speed up in all the other data sets, right? Yeah, in all the other 6 data sets we get a speed up, we do not get a speed up in east and word net. So now that we have 15 different machine learning algorithms, what we are going to do is consolidate the results in using an ensemble method. So this is what we get the speed up using the ensemble method on the right. Yeah. On the left. So what we observe here is this. Patents has the highest speed up, followed by EU 2005, then almost equal speed up in DBLP and human, and we have a degradation in performance when in the east and word net data set. Now we observe that the east data set, which has a degradation in performance, also has the lowest number of data vertices. Okay, the word net data set, in which we have the lowest accurate speed up, has the lowest number of levels, has the lowest number of count in which we were able to complete execution within the given threshold. Right. So, in contrast to this, we observe that the highest accuracy that we get is in patents data set. This has the highest number of vertices. Okay. Yeah. In the YouTube data set, in which we get the second highest performance, it has the highest number of edges, second highest number of vertices. Similarly, in EU 2005 and BBLP, we have a relatively very high number of edges and vertices. So there is a direct correlation. The higher the amount of data that we have to learn, the higher is the amount of speed up that we can attain. So this is what we observe, and one final thing that we observe would be this. There might be this question: why do I have all these different models for all these different data sets? For these 8 data sets, why do I have this 8 different ensemble models? Why not one single model? Why not one ring to tap out? We cannot. It's what we observe through analysis of the random forest trees. This is the feature importance using Gini index of the random forest, and this is of the GLF features, right? What we observe is that for different data set, different features are given different weightage to make the decision trees in the random forest. So if we combine them, then the specialized trees for one data set cannot be generalized to a different data set. So unfortunately, we hypothesize that for each data set we will need a different model, and we have tested this by trying to create a single model across all data set that does not perform as good as these things do. And yeah, in conclusion, this type of per instance algorithm selection has been applied in many problems like traveling salesman satisfiability, air planning, etc. Traditionally, the graph features and level features that we used have been applied. We have applied graphland features in per instance algorithm selection, and to our knowledge, nobody has done this before. We see a good performance improvement using graphlet features compared to using only graph and level feature. We see improvement in most of our data set. When we have a large amount of data, we get good accuracy. When we have less data, we get a reduction in accuracy. And yeah, we can have a larger number of data by increasing the threshold. We have a threshold of 30 minutes, but there is no threshold that we can go to because of the NP-complete nature of the problem. And yeah, this study that we did has the potential to be used in pattern searching and graph database query resolution. Thank you.
Thank you.